Good afternoon everyone. I am Chanda Devnath, one of the PMRF fellows. So I am the TA of this course Retrosynthesis in Organic Chemistry. In these classes I usually discuss about some topics which will help you to solve your assignments and also get an idea about this topic in a clear way. So in the previous classes I have discussed about some important name reactions as well as some rearrangements which are really required for designing retrosynthesis of any compound. So today also I will discuss some remaining reactions which have been mentioned again and again in your assignments. So let's start. So today we will discuss about some important concepts or name reactions like Barton, nitrile, photolysis. All these name reactions have been mentioned in your assignments as options or as a how to perform any reaction. So this name reaction has been again and again repeatedly used. So you should have a clear idea which name reaction leads to which type of product and what is the mechanism behind that, so that whenever a reaction is given to you, you can get an idea. Okay, my product look like this, and from this type of substrate, if you are getting this type of product, which name reaction should we apply? So here I have taken some important name reactions which have been again and again mentioned in your assignments, previous assignments. So I think after in the previous classes also I was discussing about all those. After this, I think almost I have covered almost all the reactions which have been mentioned in your assignments. From the next week we'll discuss about some different type of concept which will help you to solve your other assignments. So first today we'll discuss about Barton nitrile photolysis reaction. So here I have tried to, in your assignment they have basically mentioned about this Barton nitrile photolysis, but along with that in this class I'm trying to discuss all these three Barton reactions which have been discovered by the same scientist Derek Barton. He's a Nobel laureate. He got a Nobel Prize for designing this organic compound synthesis. So one is Barton nitrile, Barton decarboxylation, and another is Barton Maccombie deoxygenation. Why I am mentioning all the three in a same class, so that you don't have any confusion about which reactions should we perform, because there are three type of reaction, and sometimes as the same scientist name has been used for these three reaction, we make a confusion and we end up taking the wrong answer. Then we will discuss about some 3,3 sigma-tropic reactions like Ireland and Claisen reaction. Here I haven't mentioned, actually we'll discuss about some another two types of 3 sigma-tropic reaction, and then we will discuss about yin reaction. So let's start. First is Barton nitrile photolysis. So what is Barton nitrile photolysis? The Barton reaction, also known as a Barton nitrile photolysis, is a photochemical reaction that involves the photolysis of an alkyl nitrile to form a delta nitroso alcohol. So it was discovered by Nobel laureate Sir Derek Barton, and he got a Nobel Prize in 1969. and for his work in understanding conformations of organic molecules, which was the key of realizing the utility of Barton reaction. So there is a very unique concept in this reaction. Here you can see if you are taking a alkyl nitrile compound, this is a nitrile group, alkyl nitrile compound, and if you perform this reaction under photochemical condition, what happened? The delta hydrogen with respect to this nitrile group with mark alpha, beta, gamma, and this is delta. This delta hydrogen get abstracted and this group shifts from here to this delta carbon group, and after that through tautomerization this comes here. So this reaction is very selective towards the delta hydrogen. So if you want to functionalize, suppose by this one, this was just a remote CH bond. This was a remote CH bond. There is no adjacent functional group adjacent to this one. This remote CH bond can be functionalized by this one. You can make it a ketone, and after ketone you can make it a double CH2 and anywhere. So by this process you can functionalize a remote CH bond. Okay. So due to its unique property at the time to change otherwise inert substrate, Barton used this reaction extensively in 1960s to create a number of unnatural steroid analogues. So what is the mechanism behind this? The Barton reaction involves the homolytic cleavage of nitrile group. Homolytic cleavage of this nitrile group. What happens? There is a homolytic cleavage along this ONO bond and generates this radical. Then this radical abstract selectively the delta hydrogen. This is delta hydrogen. Selectively the delta hydrogen, and this radical shifts to this delta position. After that, in medium this NO radical will combine with our carbon radical and give us this nitroso compound. First it will give, then free radical recombination, then tautomerization to give form an oxime. Nitroso, this is nitroso. And through tautomerization we will get this oxime. Selectivity for the delta hydrogen is a result of the conformation of 6-membered radical intermediate. So as this selectively abstract this delta hydrogen, so we end up getting a 6-membered radical intermediate. So this is a 6-membered radical intermediate. So what is the application of that? By this methodology we can functionalize selectively the delta carbon. We can functionalize selectively the delta carbon. So here you can see this is steroid compound is given. In this one there is a wedge. After that they are adding NOCl forming this nitrile form of this ONO. Then if we are applying a photochemical condition, what will happen? What will happen? So under this photochemical condition, there will be a selective functionalization of the delta hydrogen. So there is which is the delta position, alpha, beta, gamma. Now there are three type of delta position. This one is delta, this one is also delta, and this one is also delta. But now you can see this delta hydrogen is more available to abstract because these rest two are involved in the ring. So there can be a strain because of that. Because of that, this radical will after that it will form, if you will go through this type of intermediate, it will form a O radical. This O radical will abstract proton from this position and generate a radical here. Then this radical will combine with NO radical, forming this nitroso compound. After that, through resonance, it will form this oxime type of compound. If we add Ac2O, it will be OAC. Then if we add NaNO2, what will happen? In presence of 5% NaNO2, this part will be acidified to form a carbonyl compound. It will form a double bonded O. 5% NaNO2, it will form a double bonded O. After this in medium OH will attack in medium OH will attack at this position, forming this cyclic compound. Okay, so this is the application of Barton-Nightingale photolysis reaction. Next is Barton decarboxylation reaction. So Barton decarboxylation is a radical reaction in which a carboxylic acid is converted to a hydroxamate ester, commonly known as Barton ester. The product is then heated in presence of radical initiator and a suitable hydrogen donor to afford the decarboxylated product. This is an example of reductive decarboxylation, and using this reaction it is possible to remove the carboxylic acid with a moiety from a alkyl group and replace them with other functional group. So if you see the reaction, in general reaction, what happens if you are reacting this carboxylic acid with a with a thio type of compound to form this thiohydroxycarboxymate ester, and if you are adding a radical initiator, this AIBN is a radical initiator and a hydrogen donor, what happens? This undergoes this radical initiator will cleave this Bu3SNH to form tin radical. This tin radical will attack to this sulfur atom. This bond comes here. generating R dot and this one. Now this R dot will take a proton from this radical initiator forming this RH. Okay. Next, what is the mechanism of this reaction? As I have already discussed, let's take a look again. So this will attack to the sulfur. This bond will break, forming this R radical. Now this R radical will take a proton from this hydrogen donor and give us RH. Now instead of this one, if there is any halogen source, what will happen? This radical will attack to this halogen source, forming RBr. Okay, so by just changing the, if you adding some other type of groups, then instead of taking proton from the hydrogen donor, it can react with that and the carboxylic group can be substituted with other functionality. Next type of Barton reaction we will discuss, that is Barton-McCombie deoxygenation. So what is that? Barton-McCombie deoxygenation is an organic reaction in which hydroxyl functional group in an organic compound is replaced with a hydrogen. So it is similar to the Barton decarboxylation. In that Barton decarboxylation, what is happening? The carboxylic group has been replaced by other functionality. But in this case, the hydroxy group will be displaced by any hydrogen or any other functionality. So what will happen? In that case, we are forming a thiohydroxy carbonyl type of ester. But in this case, if you react with this chlorothionyl chloride, this so not thionyl chloride, this if you react with this thionyl chloride, then what will happen? This OH will here, just like acyl chloride, it will react just like acyl chloride. Instead of oxygen, there is just sulfur. Form this. If you add this in radical in the similar way, what will happen? This radical initiator, in this one you can understand it simply. This, it will generate the radical like the previous one, and this radical initiator will attack to this sulfur atom, forming this R radical, and when this R radical will take up a proton from this hydrogen donor, giving us our desired RH. So what is the difference of Barton decarboxylation? Here there the carboxyl group is displaced by hydrogen or any functionality, but in this case of Barton-McCombie deoxygenation, what happens? The OH group is displaced by hydrogen or any functionality. Next, we will discuss about C3 sigmatopic reaction. In the previous classes, we have discussed about some cycloaddition reaction like the Diels-Alder reaction we have discussed in the last class. We have discussed about 2+2 cycloaddition reaction and De-Mayo reaction. We have discussed about 3 important cycloaddition reaction. So in this class we are discussing some sigmatropic reaction. In the previous class I have also talked about that photocatalytic photochemical reactions are 3 types. First one is or pericyclic reactions are three types. First one is cycloaddition, second is sigmatopic reaction, and third one is sorry, I don't. So in this class we will discuss about 3,3 sigmatopic reaction. So the another important type of 3,3 sigmatopic reaction is co-prearrangement. So what is happening in co-prearrangement? The co-prearrangement is an extensively studied organic reaction involving 3,3 sigmatopic rearrangement in 1,5-diene. So this is a 1,5-diene. Why 1,5? If you consider this as a 1, sorry, not this. You consider this as a 1. According to UPAC rule, you have to take the numbering where you can get the functionality at first. That we have no. So the numbering will be from this side, because otherwise the functionality will get 4 if we give numbering from this side. But if you give numbering from this side, the functionalized carbon will get number 3. So we will give the numbering from this side. So this is a 1,5-diene. So if you give heat to this reaction, what will happen? In that case you have to, this is a 1,5-diene, but just for your easier to understand what is 3,3 sigmatopic reaction, the numbering should be in a different way. Then across the sigma bond the numbering will be 1, 1, 2, 2, 3, 3. So what will happen in this 3,3 sigmatopic reaction? The bond between 1, 1 will be broken and a new bond will be formed between 3 and 3. So let's start. So this part will go here. This attack in this position. This double bond will shift, giving us this as our product. Understood? In 3,3 sigmatopic reaction you have to give numbering in such a way that you have to put 1, 1 across the sigma bond, then 2, 2, 3, 3. So in the sigmatopic reaction the bond between 1, 1 will be broken and a new bond will be formed between 3 and 3. There are some other type of 3,3 sigmatopic reaction which have been application of this. So first one is Ireland-Claisen rearrangement. This name has been mentioned again and again in your assignments. So for this clarity, I am mentioning what type of substrate you will consider this. We know about Claisen rearrangement, but Ireland-Claisen rearrangement is not that much famous. And if you are there is just difference in the nature of the substrate. So just by looking at the nature of the substrate you can check that if it is Ireland-Claisen rearrangement or not. So it is applicable for allylic ester with a strong base to give us gamma delta unsaturated carboxylic ester. So let's start. So you have to give numbering 1, 1 across the sigma bond. So if you give this is 1, sorry, not this is ester, then there will be if you add a strong base. Without strong base it will not form. If you add a strong base, this CH3 proton will be abstracted and this goes here, forming this enolate type of compound. Now see, this looks like 1,5-diene. This looks like 1,5-diene. Now you can give the numbering. So what will happen? This 1, 1 bond will be broken. This goes here. In presence of H plus, this OLI will be hydrogenated and we will get this as our product. Okay. So if you are having any allylic ester, and in presence of strong base, in presence of strong base, it will be this hydrogen will be abstracted, forming this enol type of compound, and after in presence of heat it will undergo this 3,3 sigmatopic reaction, forming this gamma delta unsaturated carboxylic acid. Next is the Overman rearrangement. This is also another type of 3,3 sigmatopic reaction. This is a chemical reaction that can be described as a Claisen rearrangement of allylic alcohol. So this was for allylic ester, but this is for allylic alcohol. So you have to remember the difference. Suppose in some question there is also given that it is coke or Claisen or Ireland Claisen or Overman. There is a very thin line between all these three, because mechanism is same for all these four. All are 3,3 sigmatopic reaction, but one is for 1,5-diene, simple 1,5-diene. Ireland Claisen is for allylic ester, whereas this Overman rearrangement is for allylic alcohol. So if you treat this allylic alcohol with trichloroacetamide to form this allylic trichloroacetamide, then after this reaction is this base will take up a proton from here, then O- will attack at this position. It will open up. Now it's look like a 1,5-diene. Now it undergoes a sigmatopic reaction. Forming this as our product. Okay, so we have discussed three type of 3,3 sigmatopic reaction. So what is the mechanism of this all three? All three have been going through a 6-member transition state. All these three are going through a 6-member transition state, because this is coming here, Zimmermann-Taxler transition state. 6-member transition state means that is called Zimmermann-Taxler transition state. So it is going through a Zimmermann-Taxler transition state. So if there is one example is given how this can be formed. So it is an example of cope reaction. So see this, if you give a numbering, the bond between 1,1 is getting broken, and there is a new bond, sigma bond formation between 3 and 3. So let's solve some question based on this theory. So we have discussed about, so here what is given, ONCl and HNO. Wherever there is ON and HNO is given, you can get an idea it can be a Barton nitrile photolysis reaction. So let's try to do that. So this OH will attack to this NO and eliminate this Cl from the system, forming this nitrile compound. I am writing this NPTEL as a R only. Okay, so after that, if you add a photochemical condition, what will happen? This will be cleaved, and the hydrogen with respect to this delta position, this is alpha, beta, gamma, delta. If you give numbering from this side, this is alpha, beta, gamma, delta. Now you can see, if you want to abstract a proton from this side, from the same ring, there will be a huge strain, because to get that transition state, you just try to imagine this in a 3D. To abstract a proton from this position, this O should bend in such a way and go towards this hydrogen to abstract, whereas this hydrogen is closer to that OH, that O dot. Okay, to reach to this hydrogen, this O has to be bent down to go towards this hydrogen, but in this case this hydrogen is bit closer to this carbon. That's why this delta hydrogen will react, not this one. So this will be OH. Now through nitroso-oxygenate tautomerism, it will form this type of oxygen compound. Okay, understood? So this is the application of Barton NPTEL photolysis. Now next is this one. So here after this reaction we will get A, and then we will get B. So you have to denote A and B. So here one ester type of compound is given. So there is a oxygen. So what will happen? This will form the, it will react with this and remove one of the imidazolium group, imidazole, from the system, and forming this. So both will be formed, two imidazole type of system. Now we know in case of Barton McCombie dehydroxylation reaction, what happens if you add a radical initiator and a hydrogen donor? What will happen? The OH will be substituted with H. So all these two will be cleaved like radical initiator. Sorry, not from this position. This is all. So this radical initiator will attack to this position, and this goes here, and it will break like similar way, and will as a product, in this case also the radical initiator will attack here, this comes here. If you have any confusion, you can go the previous slides and check the mechanism of the Barton deoxygenation reaction, then you can get an idea. I'm not doing the mechanism again and again. Then we will get our product as like this. Just our OH group will be substituted with H. This will be also H. Our OH group will be substituted with the H. So this will be our A, where the OH group will be esterified, thioesterified. Then it will be our B, where the OH group will be substituted by H. Okay. Next is this one. So if you see the product, just heat is given. Now you can see this is one, looks like a 1,5 diene if you give a numbering. This is 1, 1, 2, 3, 2, 3. So let's try to do the 3,3 sigmatopic type of reaction, if it matches with our product or not. This comes here. This will attack to this position. Then what will be our product? There will be a double bond, OMe, this will be connected to this center. Now this is, let's count the number of ring. So this is 6 member ring, this part is a 6 member ring, and this part 1, 2, 3, 4, 5, 6. This is part also a 6 member ring. So there is a 6, 6 fused ring, fused from this position. The common 2 carbons are these 2. Draw it properly. So these 2 carbon are common. 6 member ring, and adjacent to the 6 member ring there is a double bond. This will be OMe. If you give a numbering, this is 1, 2, 3, 4. Just to draw the compound, this will be 1. This will be 1. Sorry. This will be 4, 5. So if we have already 1, 2, 3, 4, 5. So this will be OH. And there will be a double bond, and through tautomerization we will get this as our product. Okay. Next we will discuss about in reaction. So in organic chemistry, the in reaction is a chemical reaction between an alkene with a allylic hydrogen and a compound containing a multiple bond. In order to form a new sigma bond with a migration of the in double bond and 1,5 hydrogen shift. The product is a disubstituted alkene with a double bond shifted to the allylic position. So here you can see this double bond, there is a allylic hydrogen react with a double bond. So you can compare this like a 4+ to cycloaddition type of reaction. So if you consider this as a diene and this as a dienophile, so it is attacking to this H, this bond breaks, then it also attacks to this double bond and forming this as our product. So what is the mechanism? So how this reacts? So this homo part of this allylic hydrogen, this part will attack to this LUMO of this dienophile and form through this 6-member transition state. It will give us this as our product. Now this can be applied instead of this double bond, we can use a triple bond also. So what will happen in that case? So here two conditions are given. One is if you are heating it to 220 degree, and if you are adding in Lewis acid, then heating can be decreased to 25 degree also. So there are two types of conditions. This is like or. You can do two conditions, this or this. So what will happen? From the arrows you can get an idea. Sorry. So this hydrogen bond get broken and this bond gets shifted to this place, and there is a new sigma bond formation, and this bond is become a double bond and get hydrogenated from. So this, if you mark this hydrogen, so this hydrogen shift to this position, forming this as our product. Okay. Another example, let's try to solve this one. So this is, if you consider this as the allylic hydrogen donor and this as the dienophile, what will happen? So obviously this part will attack to this, and this OH will have oxygen will abstract the proton from here. This comes. So let's try to draw the product. So this will be our product. Okay. You know now what is OTBS? This tributyl silane. This has been discussed in previous classes, where we have discussed about the protecting group, deprotecting group. In the previous class, if you want to know how to remove this OTBS, you can go to the last class and get an idea that how to remove this silyl type of ether, how to remove these silyl ethers. The previous class we have discussed about that. So next is Konya-in reaction. In organic chemistry, the Konya-in reaction is an intramolecular cyclization reaction between an enolizable carbonyl such as an ester or ketone and an alkyne or alkene, giving a cyclic product with a new carbon-carbon bond. This type of this reaction has also been mentioned in your assignments multiple times. So to get an idea what is the difference between, sometimes you can get a confusion that in reaction and Konya-in reaction are same, but no, in and Konya-in reactions are not same, both are quite slightly different. So this is the, so in this case what will happen, it will attack So imagine that this it will attack here and forming this as a product. So if you try to solve this as a mechanism, as a some example, what will happen in this one? Just try to, I am trying to draw the product directly. What will happen? If there is a double bond, then this double bond carbon will, if you have to join this one directly, and then this double bond will be a single bond now. It can be applied for triple bond also. What will happen? This triple bond will attack to this position, and now this triple bond will be now a double bond. One bond will be decreased because there is a new bond formation. Okay, so this is the difference between Konya-in and in reaction. Whenever you can see this type of product formation, what will go? You will go for Konya-in reaction. So now we will discuss about some previous year question which came in GATE and NET. These are not totally related to the topics we have discussed, but all this topic has been discussed in the previous classes. I am just this is the compiled version of that one. So based on all the classes, I am trying to solve this question, so you can get an idea that how much we have learned till now. So how much we can get an idea that which type of reagent will give which type of product. So they have asked the reaction in which inversion of configuration occurs. In which reaction a inversion of configuration will be take place. So this is date PPSC we have discussed about this. This is Mitsunobu reaction. This is a Mitsunobu reaction. So in Mitsunobu reaction what happens? The stereochemistry of this OH group get altered and we get a ester in the opposite side of this opposite. From this one we will get a ester in the above the plane. So there will be an inversion of configuration. This is a just this is undergoes a is a concerted reaction. So one type of pericyclic reaction. There is no question of inversion of configuration. So this is already out from the option. There is no question of inversion of configuration. It is which type of reaction? This is Hoffman degradation reaction. This is a Hoffman degradation reaction. What happens in, we have discussed about this also. What happens in, so you have to, just by seeing the reagent and substrate, you have to get an idea which type of reaction we have to perform. So if there is a amide group and we are adding NaOBr, what will happen? This will be a Hoffman degradation reaction. In that case, it will be just INH2. CO will be, there will be, so there is also no question of inversion of configuration. This is also out. Now in this case, which type of reaction we perform? There is a PAR acid is given. So whenever there is a PAR acid, what we will perform? We will perform Baeyer-Villiger oxidation. So in case of Baeyer-Villiger oxidation, we know there will be oxygen incorporation. One of the group will be shifted and we will get a oxygen. So you know about the mechanism. There is a this type of transition state. We have discussed about this also. Just go the previous classes and check. In Baeyer-Villiger oxidation, if there is a carbon-carbon bond, like this way, one of the bond will get shifted to this position, one of this bond will get shifted. So which will be shifted, that depends on the shifting property, and we know that tertiary group has better shifting property than primary, so this group will be shifted, but this is totally concerted. The shifting is totally concerted. During this shifting, the stereochemistry of this carbon will not be changed, so it will be same. So there is also no question of inversion. There will be a there will be no question of inversion of configuration. There will be also just a shifting, retaining the stereochemistry of this carbon. So just by, as we have solved all this type of name reaction, so we can solve these problems in a single chance. So there will be no inversion of configuration also. So the correct option will be only option A. The correct option will be option A. So this is pericyclic reaction, this is Hoffman degradation reaction, this is Baeyer-Villiger reaction, and this is Mitsunobu reaction. So you have to know all the type of named reaction, so that if you don't know about the Mitsunobu reaction, you don't get an idea, right? PPST date, what will happen in this reaction, what will be the product. If you don't know the product, how can you determine that there will be an inversion of configuration or a retention of configuration? Here also, if you don't know about the reagent of the Baeyer-Villiger oxidation, and if you don't know about the migrating property, you can't get an idea that okay, what will be the stereochemistry of the product. So you have to know about the name reactions. Next is this one. This is also a name reaction we have discussed about. Can you get an idea? So this is a silicon compound. So it's not an name reaction actually. This is a benzene. It will be a formation of benzene. So there will be a formation of benzene. We will try to discuss this topic in the next. So this is an old topic. There will be a formation of benzene. So this goes here. Now if you add so this can to one of the benzene carbon to so there will be a pH with a positive charge here, and there will be another pH and there is another H is available. So the correct option will be option A. The correct option will be option A. Let's go to our next question. So in the following reaction, what will happen? What will be our X and Y? So in presence of strong base, there will be a proton. It will be abstracted, forming an anion. So this anion will attack to this position, giving us, suppose this is a alpha beta unsaturated compound, it's giving us this as our product. Giving us this as our product. So our X will be this one. So first two are already out. First and third, fourth one are already out. Now if we add xylene and H2Cl2, in presence of H2Cl2, what will happen? Now in presence of xylene and reflux, there will be a H, this comes here and this group will be eliminated, and in the second step as HgCl2 is given, so this will be deprotected. We know about protection, deprotection. We have talked in the last class how to deprotect this type of group. So in presence of deprotection, so you will get this as our product. So the correct option will be option C. Okay, let's go to the next question. This is also, this is, we know about this one, the like Chugev, not Chugev actually, I don't actually forgot the name of the reaction. You know about the sulfurylide. So this is sulfoniamylide and this is sulfoxoniamylide. So you know the difference. In presence of sulfoniamylide, if there is a carbonyl compound, that will give a epoxide. In presence of sulfoxoniamylide, if there is just a carbonyl compound, it will also give a epoxide. But if there is a alpha beta unsaturated compound, the sulfoxoniamylide will selectively react with the alpha beta unsaturated double bond. So in presence of sulfoniamylide, it will just react with the carbonyl compound. Selectively it will just react with the carbonyl compound. So it will give us epoxide. So which will be the product? B. But in case of sulfoxoniamylide, it will selectively react with the, in case of sulfoxoniamylide, it will selectively react with the alpha beta unsaturated double bond. So our product will be this one. So both of them are same, giving the right, so the correct option will be option B. Okay, so if it is sulfoniamylide, it will selectively react with the carbonyl compound to give a epoxide. But if it is a sulfoxoniamylide, if there is only just a carbonyl compound, this will also give a epoxide. But if there is a alpha beta unsaturated carbonyl compound, then in that case it will react with the alpha beta unsaturated double bond. Now if in this compound we are giving CH2N2, what will happen? I'm just adding another. If we adding CH2N2, what will happen? In that case we will form a cyclopropane. In that case it is selectively react with the electron rich double bond. So which double bond will react? In that case this part will react. The lower double bond will react, not upper two. Okay, so you have to know the difference, which to react which group, what type of reagent we have to given. So in that case we will get this double bond will be unreacted, the carbonyl group will be also unreacted, but the lower double bond will react in presence of CH2N2. So thank you, this much for today's class. I hope I have tried to cover up all the name reaction which have been discussed or in your assignments. So if I will check again, if 1, 2 are, I have almost completed all the name reaction as much I know. But if 1 or 2 are left, we will discuss those in the next class. Moreover, we will discuss some new topics, new concept which will help you to attempt your assignments. So thank you for today's class. We'll meet you in the next class, the same time. Thank you.